In this lesson, we are going to be finding rational zeros, and we will use the rational root theorem to be able to find all the solutions of a polynomial function. So, when we are looking at polynomial functions and being able to find all the rational zeros, the first thing we're going to be asking you to do today is to make sure that the polynomial has all integer coefficients. Then we are going to first find all the possible zeros for that polynomial function by using what we call the rational root theorem. And the rational root theorem says that all of the possible zeros or solutions of the polynomial function are found by taking the factors of the constant term and dividing them by the factors of the leading coefficient. Let's take a look at an example. So here's our first polynomial. We have x cubed minus x squared minus 9x plus 9. When we take a look at that polynomial function, the first thing that we want to notice is that it is written in standard form. Then secondly, what we want to make sure is that all of the coefficients are integers. Now what we're going to do is we're going to find all the factors of the constant term. So the constant term is 9, and so I want to find all the factors of 9. All the factors of 9 would be 1, 3, and 9, but we do want to make sure that we list all of the factors, so we could have a positive or a negative 1, a positive or a negative 3, and a positive or a negative 9. Remember, the factors are what we multiply together to get our product of 9. So we could have 1 times 9 or negative 1 times negative 9. 3 times 3 or negative 3 times negative 3. And then we need the factors of our leading coefficient. And our leading coefficient is 1. So this is an easy one. The factors for 1 would just be positive or negative 1. So to find all the possible solutions or zeros of this function, we simply take all of the factors of 9, positive and negative 1, positive and negative 3, and positive and negative 9, and we divide that by the factors of the leading coefficient, which is 1. So our factors, or all of our possible zeros or solutions for this polynomial, could be positive or negative 1, positive or negative 3, positive or negative 9. So in a minute, what we're going to actually do then is test some of these possibilities to find a zero using synthetic division. Let's take a look at another example so that we can practice finding all of the possible rational zeros of the function. So the first thing we're going to do is we're going to find all of the factors of our constant term. So our constant term is 6. Again, making sure that our polynomial is written in standard form and that all of the coefficients are integers. So first we're going to find all of our possible zeros. So the factors of 6 would be positive or negative 1, positive or negative 2, positive or negative 3, positive or negative 6. And then we would divide that by all the factors of our leading coefficient, which is 1. So when we divide all of those by positive or negative 1, we end up with our same list. So these are all the possible zeros that we could use to test. Now the problem occurs quickly that the more factors we have for each of these, the more possibilities that there would be. In this instance, we have 8 possibilities, and so that can become a problem of having to test so many different rational zeros. So here's the other thing that we would recommend that we do. What we would recommend is now plotting our polynomial function with our graphing calculator. So remember, to do that, you're going to press the y equals button and enter the polynomial function into your calculator. Then you press graph. And so what we can do then is we can estimate what the zeros are for our polynomial function, and at least be able to find one and then be able to take a look at some more. So if we take a look, it looks like here we have a fraction and here we have a fraction, but here our function is crossing right at positive 3. So we can use positive 3 or x equals 3 as one of our zeros or solutions, and we can use synthetic division to find the rest. So we're going to divide our polynomial function using synthetic division by 3. So we list the coefficients and do our synthetic division. And so we find out that 3 is a solution. So now what we can do is rewrite our remaining coefficients for our polynomial x squared minus 4x minus 2 and set that equal to 0. The first option we would want to take a look at is factoring, and that's not going to work in this particular instance. So since it isn't going to work, we will use the quadratic formula. So we have x equals our negative b which would be 4, plus or minus the square root of b squared, which would be negative 4 squared, minus 4 times our a, which is 1, times our c, which is negative 2, all divided by 2 times a, which is 1. So we have x equals 4 plus or minus the square root of 16 plus 8, which is 24, divided by 2. Then what we want to do is we want to simplify to find our roots. So if we were to make a factor tree for 24 and decide what would come out of the root, we would have 4 times 6, 2 times 2, 2 times 3, which means that the square root of 4 can come out of the root. So we have x is equal to 4 plus or minus 2 square roots of 6 over 2. And so dividing all of our terms by 2, that would equal 2 plus or minus the square root of 6. So our three roots are x is equal to 3, and then we have 2 plus or minus the square root of 6. So you can tell that that is where our other two roots are crossing at those particular points, which will end up being decimals. Let's take a look at another example. So we want to find all the possible zeros for this function. First of all, we want to find all the factors of our constant term. So we would have plus or minus 1, plus or minus 2, and plus or minus 4, which is going to give us all of our factors of 4. Then we want to divide that by all of the factors of our leading coefficient. So we have plus or minus 1, plus or minus 3, plus or minus 5, and plus or minus 15. Again, we should have made sure that our polynomial is written in standard form and that we have all integer coefficients. Now, if we are now to list all of the possible zeros, we're going to have to do this in an organized fashion. So we're going to start with taking our numerator divided by our first part of our denominator. So plus or minus 1 divided by plus or minus 1 would give us plus or minus 1. Plus or minus 2 divided by 1 would give us plus or minus 2. And then when we take our 4 plus or minus divided by 1, we have plus or minus 4. Then we want to divide each of the numerators by our second set of factors in the denominator. So we're going to have plus or minus 1/3, plus or minus 2/3, and plus or minus 4/3. Okay? Then we are going to take our numerator factors and divide it by our next denominator factor. So we have plus or minus 1/5, plus or minus 2/5, plus or minus 4/5. And then we take our numerator factors and divide by the last denominator factor. So we have plus or minus 1/15, we have plus or minus 2/15, and we have plus or minus 4/15. Now we even see a greater need of taking a look at what our polynomial function looks like on the graphing calculator in order to be able to narrow some of these solutions down. So if we take a look at an enlarged version on the graphing calculator, it can be kind of difficult to see where these are at. So we have something that's less than 1 or closer, or less than 0, closer to -1. And then we have something that's just past our 0. And then we have something just a little bit more than 1. So if we take a look, this is fairly close right here to 0 on the x-axis. So we could have something like 1/3 or possibly 1/5 or 2/5. So since it's really close, why don't we take a look at using positive 1/5. Now you can use a decimal if you'd like, and that might be easier for us to do with our synthetic division. So we're going to take and convert the 1/5 to a decimal, which is 0.2. And let's decide if that's going to work by using synthetic division. So our leading coefficient is 15, and then we're going to list the rest of our coefficients. We have -68, -7, 24, and -4. And then we're going to use synthetic division to see if this is a solution. So we bring down our 15, and then we multiply 0.2 times 15, which is 3. And we're going to add the two together. We get -65 times 0.2 gives us -13. Add those two together to get -20. Multiply that by 0.2, that gives us -4, which is a +20. And multiply that by 0.2, that gives us a +4, which our result is 0, meaning that that is a solution. So one of our solutions so far is x is equal to 0.2. Now if we take a look at another solution, take a look at our, at our remaining polynomial after we've had our synthetic division. We have 15x cubed minus 65x squared minus 20x plus 20. And we set that equal to 0. So we need another solution to test. So since I already used the 0.2, I could move over just a little bit further, and we see that it's crossing right around a little bit after 1, and if we go less than 0, we see that it's crossing pretty close to -1. So let's take a look at something that's pretty close to -1, but actually before that. So it wouldn't be 1, 2, 4, 1/3. Possibility could be 2/3. We could try 4/5, that's a little bit closer, and it looks like these 15s wouldn't be quite there. Why don't we take a look at negative 2/3 and see if that would be a possible solution. So let's try synthetic division with negative 2/3. We won't convert that to a decimal since it's a repeating decimal. So we have our coefficients of 15, negative 65, negative 20, and positive 20. So we'll bring down our 15. Multiplying negative 2/3 times 15 gives us a negative 10. And then multiplying negative 2/3 times negative 75 gives us a positive 50. Times negative 2/3 will give us, or when I add them together, I get 30. And when I multiply by negative 2/3, that gives me a negative 20 with the result of 0. So that would then be another solution. So we have x is equal to negative 2/3. So when we rewrite this particular remainder, we have 15x squared minus 75x plus 30. Now we can take a look to see if that can be factored, or we can use the quadratic formula. So what we will want to do, since it can't be factored easily, is to use the quadratic formula to finish solving. Alright, so we have 15x squared minus 75x plus 30. So we're going to use the quadratic formula to finish solving. So we have x equals negative b, which would be 75, plus or minus the square root of b squared minus 4 times a times c all over 2 times a, which is 15. So to save a little time, I squared negative 75, and then I multiplied negative 4 times 15 times 30, and subtracted the 2 to get 3,825. So when we simplify that particular root, we find out that there is a perfect square contained in 3,825, which is 225. So when we bring that out, the square root of 225 would be 15. So we have 75 plus or minus 15, square root of 17, all over 30. And we can see that all three terms can be divided by 15. So 15 goes into 75 5 times, plus or minus 1 square root of 17, all over 30. So along with the other two solutions, which was a positive 0.2 or 1/5 and a negative 2/3, these would be the other two solutions. So in review, what we would like to do is to make sure we are finding all the possible zeros of the polynomial by using the factors of the constant term divided by the factors of the leading coefficient, as long as all of the coefficients of the polynomial function are integers. Test one of the solutions by using synthetic division, and from there you may need to use more synthetic division, or you might be able to factor and solve your remaining polynomial. You may need to use your graphing calculator to estimate which zeros to test. Please be sure to complete the reflection.